So what is a parameterized reduction? Suppose we are giving a parameterized reduction from problem A to problem B. Now let me use terms like, let's say I is an instance of problem A. Now what's an instance of problem A? For vertex cover it's G comma K. For satisfiability, like for max the decision version of satisfiability, it will be some formula phi comma K, like that. That's the problem instance. And because we're talking about parameterized problems, there is always a parameter associated with it. The kind of parameters that we had seen so far were the parameters which were the size of the solution. For example, if we were looking for a K size vertex cover, it was K there. If we were looking for a K path, it was K there. But in general, the parameter could be anything, right? So given a parameterized problem, it will be of this form. There will be an instance and then there will be a parameter. Given this instance of A, and if suppose we are able to reduce this instance of A into an instance of B, which is like some I prime P prime, and we are able to reduce it in time f of p. Now p is the parameter, okay? F of p into some polynomial function of the instance size. If we are able to give a reduction from problem A to problem B in this much time, such that the instance that I have created of B prime has size some g of p into this, and the parameter p prime is again some function of p alone. If I am able to give a reduction of this kind, like with this property, the time taken for reduction is this, the output instance has this size, the parameter p has this size, then I am saying, then I can make the following claim. If this happens, then we can say that if B is FPT with respect to parameter P, that means B has an algorithm that runs in time, again I am using F here, it's just saying that runs in some FPT time. Then my claim is if B has an algorithm that runs in this much time, then A is FPT with respect to parameter P. That means A has an algorithm that runs in time some f of p into polynomial in n. Again, as I said, these f's might not be the same. It's all I want to say is, or let me just write f of f prime here and f here. Okay. Again, why is this true? Suppose B is FPT, so B has such an if B is FPT, then B has such an algorithm. If B is FPT, then B has such an algorithm. Then how can we give an FPT algorithm for A? We'll do this reduction. Given an instance of A, we'll do this reduction. It will take f of p into polynomial this much time, and in this much time we'll reduce it to this instance of B, and then we'll apply this algorithm there, right? So the total time taken would be, so the total time taken to solve the problem B would be this f of p time, which is used for the reduction, plus this f prime p prime time. But what is p prime? P prime is some function of p again. So it is some h of p into I prime, polynomial in I prime time, and I prime is gp, so some polynomial in this and some polynomial in I, right? So this is like a huge running time that I have written, but the takeaway here is what is this running time, what is the form of this running time? Note that this whole thing is some function of p alone, right? And this is some polynomial function in the size of the input alone, right? And again, this is f of p and this is polynomial in n. So the whole algorithm runs in time, again I am using f again, it is some f of p right? So if I have such a reduction, then we can always give this, right? And hence, if we have to prove that a certain problem is not FPT, if we start with a problem A that is known to not have an FPT algorithm with respect to a particular parameter P, then if we can give such a reduction, then we know that B cannot have an FPT algorithm with respect to this parameter P prime, right? The same as the NP hardness corollaries that we get. Make sense? Okay. So again, we have done a lot of complicated things, not really a lot of complicated things, we have just pointed out that what exactly do we need from a reduction so that we could lift negative results, negative FPT results of certain problems to negative FPT results of other problems. When I say negative FPT results, as in these problems don't have FPT algorithms, those kind of results, okay. And see, again, the point to note is, these two properties, if you see, these are like the properties that, these are the kind of properties that you would want in an NP hardness reduction also without these terms. You would want the reduction to be polynomial time reduction, and you would want the output instance to be some polynomial in the input instance, right? We could have also written that, if we had that, then also this is a parameterized reduction. It's just that we have an extra leverage. So for certain kind of problems, you might want to take advantage of this leverage that you get. But yeah, so this is the leverage, but the most crucial point is this thing, the parameter. The parameter here should, the parameter of the reduced instance should only be a parameter of the input instance. And hence, for example, if you go back and look at the NP hardness reductions that you have seen, okay, so this could be a good exercise. See which of them are parameterized reductions and which are not. For example, clearly the NP hardness reduction that you had seen for 3-SAT to vertex cover, that is not, right, because as you just said there, in the reduced instance we are looking for a vertex cover that has size something, but that depends on the number of clauses in the SAT formula, right. So again, one good exercise is go back, look at all those exercises and see which of them are parameterized reductions, and if they are not, try to see, can you make them parameterized? So of course, when I say can you make them parameterized, so when you start with 3-SAT, what is the parameter there? Like the NP hardness reduction that you did, you started with the 3-SAT formula, you just started with an optimization version of the like not even optimization. You wanted to find an assignment that satisfies all the clauses, right? So of course, you have to modify the reductions in the way that, like, the reduction should be from a parameterized problem to a parameterized problem, okay. And so one standard parameterized problem is, like, look at the decision version of this 3-SAT problem. We saw a kernel for max 3-SAT, right? So there we formulated the decision version of the 3-SAT problem, and with that you can associate any parameter. One default parameter is the number of clauses that you want to satisfy. Like, you want to satisfy at least k clauses, for example, then k is the parameter. Then see if from this problem, can you give the same sort of reduction to vertex cover, which is parameter preserving. When I say parameter preserving, as in this property holds. Okay, so this could be an exercise. So what we are gonna see today, like the technical contribution of today's talk, will be a reduction from clique, a parameterized reduction from clique to dominating set. Now when I say parameterized reduction, again both the problems have to be parameterized. So the parameter for both the problems are the default parameters, by which I mean, if I am looking for a clique of size at least k, the parameter is k. In the dominating set, if I am looking for a dominating set of size at most k, the parameter is k. So given an instance g comma k of clique, I will create another instance g prime k prime of dominating set. And I want to say that, I want to claim that for dominating set has no, like, yeah, has no, okay, I should not write like this, has no f of k into polynomial in time, polynomial in n algorithm. Like, let's say if gk was an instance of dominating set, then this instance cannot be solved in this much time, where n is the number of vertices of the graph. This is the claim that I want to prove. So note that if I prove this, then yeah, so if clique was like the hardest problem in the FPT world, then dominating set is at least as hard as clique, right? Because if dominating set had an FPT algorithm, then click would have an FPT algorithm. So if click doesn't have, then at least dominating set should not have this algorithm. So okay, actually even before going to the reduction, let me throw the jargon that I wanted to throw after doing the reduction. So again, so there is the concept of hardness is a bit different in the FPT world, is what I wanted to say, in the sense that look at any NP hard problem, NP hard, okay? Look at any two NP hard problems. We say both of them are equivalent, because you can give a reduction from, let's say two problems are A and B, you can give a reduction from A to B and from B to A, right? This is true for all NP hard problems. They are all equivalent in that sense, right? Why? Because why is that so? Okay, I think I should say NP complete. That would make more sense. So if a problem is NP complete, it is in NP. So if a problem is NP hard, that means you can reduce all problems in NP to this problem. In particular, let's say we have problems A and B. So A is definitely in NP and B is NP hard. So you could definitely reduce A to B. Similarly, the other way around. A was NP hard and B was definitely in NP because it is NP complete. So you can give a reduction from B to A. In that sense, all the problems are equivalent, right? There. But in the FPT sense, there is a hierarchy of hardness. In the sense that I'll be able to give you a reduction from clique to dominating set, but I don't know of any reduction, parameterized reduction from dominating set to clique. If suppose tomorrow someone comes and gives me an FPT algorithm for clique, FPT algorithm for dominating set, definitely I'll be able to give you an FPT algorithm for clique, okay? But if tomorrow someone comes and gives me an FPT algorithm for clique, I might not be able to give you an FPT algorithm for dominating set. So the hard problems, the concept of hard problems in the FPT world, not the hard problems, they are not all equal, they are not equivalent. So there are hard problems as in, okay, or in other words, look at all the problems for which you can show that, okay, if clique does not have an f of k into FPT algorithm, then these problems do not have an FPT algorithm. But amongst them also there is a hierarchy. So they are not all equally hard. Of course, if you give an FPT algorithm for any one of those problems, you'll give an FPT algorithm for a class of problems, but you might not be able to give me an FPT algorithm for all the problems that are hard. Does it make sense? So the whole takeaway is in the classical setting, in the NP hardness setting, or look at any two NP complete problems, so they are hard for the class NP. They're all equivalent, like one can be reduced to other and the other can be reduced to the first one, but this is not the case with FPT world. So in the FPT world, there is a hierarchy of hardness also. All of them do not admit an FPT algorithm, but it's not just that. One problem is strictly harder than the other problem. Okay. So again, this is some jargon. Like if you don't get it, it's fine. So again, coming back to the goal, we are trying to give a reduction from clique to dominating set. Okay, a parameterized reduction. So, and we'll do that in a sequence of steps. Again, take that as a homework that these parameterized reductions are transitive, in the sense that if I give a parameterized reduction from A to B and from B to C, then there is a parameterized reduction from A to C, the way it works for NP hardness. Okay, so it's not difficult to prove, we can prove it. Okay, so yeah. So what we'll do is to prove this, we'll follow the following framework. We'll give a reduction from the clique problem to the independent set problem. Is this easy to see? Clique to independence, a parameterized reduction. What will be a parameterized reduction from clique to independent set? So in clique, again, you're given a graph G and integer k, you want to find if there is a clique of size k. Independent set, you're given a graph G, integer k, you want to find if there is an independent set of size k. Parameter? Yeah, so if suppose I give you an instance G comma k of clique, I can create an instance G bar comma k of independent set. Clearly, if G had a clique, if and only if G bar has an independent set. Is it a parameterized reduction? How much time does it take first of all? some poly, and you just have to look at the complement graph, right? So again, this is an f, like this is f of k into poly, like as I said, this running time definitely includes all polynomial running times, right? So this is definitely running time is okay, and size of g bar remains the same, so that is also okay, and k remains the same. K is a function, this k here is a function of the original k. So this is indeed an FPT reduction, right? And hence we have shown that even for independent set you cannot have an FPT algorithm parameterized by k. So this we have anyway already seen. So from here we'll give a reduction to something called a multicolored independent set. I'll tell you what this is. At the look of it, it looks like a very artificial problem, and yes, it indeed is a very artificial problem, but it has turned out to be a starting point for a lot of this hardness reductions in the FPT world. So like a lot of when people want to prove hardness for a certain FPT problem, this multicolored independent set is a problem. It's a natural starting point for a lot of problems, and it has turned out that if you start with this problem, you are able to give reductions to a lot of problems. So it is artificial, but it is very, very useful in the FPT world. So I'll just state what that is. So we'll give a reduction from independent set to multicolored independent set, and then finally to dominating set. Okay, so I have to give you two reductions, one from independent set to multicolored independent set, a parameterized reduction, and then a parameterized reduction from multicolored independent set to dominating set. Okay, so let's start with this one first. Okay, so before that, let me state what is this multicolored independent set problem. So in the multicolored independent set, the input graph is given to you in the, like the input graph is a very special kind of a graph. The input graph G is of the following form. Okay, I'll tell you what this is. And the input graph is given like this. So you're given k parts, each part is a click, and there could be some sort of edges going around. So the across edges I don't care, but so the input graph is given to you as the partition of the vertex set into k parts, where if you look at the edges inside any part, so this is like one part, it is a complete graph, so there are all possible edges inside each part. Okay, but the across edges, as in the edges across the parts, they could be arbitrary. Okay, this is how the input graph looks like. So when I'm giving an input to a multicolored independent set problem, this is how the input should look like. Okay, so this is the input, and together with it I'm given an integer k, and the question is, does there exist a multicolored independent set in the graph? And what is a multicolored independent set? Like, think of each of these parts Vi as a color class. So basically you want to find an independent set in the graph by picking exactly one vertex from each of these parts. So you want to find an independent set that has exactly one vertex from V1, exactly one from V2, one from V3, and so on. Okay, output, and yeah, I mean, this should anyway be true, right? Because since each color class is a click, anyways, like look at any independent set that you would give me, any independent set cannot pick more than one vertex from this click, right? So this is true. So anyway, any independent set of size k will have exactly one vertex there. If I've given you a graph in this format, I can even just say that output an independent set of size k in G. By default, the independent set that I would give you will be a multicolored independent set. In the sense, it will pick exactly one vertex from each of these. I'm calling these color classes VIs. So this is the multicolored independent set problem, and now I want to reduce independent set to multicolored independent set. So the reduction that I'm going to show you, you have seen this kind of a reduction. When we were giving a 2k kernel for vertex cover, to solve the LP for vertex cover, we reduce it to the problem of finding a matching in the bipartite graph. So we constructed a bipartite graph in a way. So the reduction is almost like that. So what is the reduction? Given a graph G here, given an instance g comma k of independent set, I'll create an instance g prime comma k of multicolored independent set, and what will be this g prime? So note that I have to give you g prime in this format. So what will be this g prime? I'll create k copies of the vertices of g first. So that will correspond to the k color classes. So what is V1 here? V1 is, let's say, the first copy of Vg. Similarly V2, V3 and Vk, like. So you created k copies of every vertex in G, and V1 is the set of first copies of those vertices, V2 is the second, and so on. And of course you make all these things a clique because that's how you want your graph to look like, right? And now how do you put the across edges? That's the most crucial part. Like, how do you put an edge between a vertex, say in this part and in this part? So suppose there was an edge uv in G, okay, you just look at the copy of u in first part and the copy of v in the second part and put an edge. So in other words, let's say if uv was an edge and you have these parts, you would have one copy in each of these parts. Let's say u1 is the copy in the first part, u2 is the copy in the second part, and so on. Similarly, v would have a copy in each part. Right? So if uv was an edge here, what you do is you put an edge between the copies of, basically all possible copies of u and v. Like, I'll put an edge between u1 and v2. I'll put an edge between them like this. I'll put an edge between u2 and v1, u1 and v3, and again v3, v1 and u3, like all possible copies of u and v, I'll put an edge. So this is the construction. So now we have to say that, okay, if there was an independent set in G, then there is a multicolored independent set in G prime, and if there is a multicolored independent set in G, then there is an independent set in G. Is it easy to see? Suppose I give you an independent set in G. Okay, suppose that independent set had, suppose I give you an independent set in G variable. So let's say I give you an independent set in G. Suppose it had vertices u, v, w and x. Suppose this was an independent set in G. What I do is I go to first color class, pick the copy of u here. So u1 I pick. Go to the second color class, pick the copy of v here. So I pick v2 here. Go to the third color class, pick the copy of v there. So v3, and so on. I'm claiming if this was an independent set, then this has to be an independent set in this graph. Why? Can there be an edge between u1 and v2? Because why would I have put an edge between u1 and v2? I would have put an edge, but if there was an edge between u and v originally, only then will I put an edge between all the possible copies of u and v, right? So if this was an independent set, this is indeed an independent set, because between no two copies would have I put an edge if there was no edge between any pair here. Make sense? Okay. And reverse direction, if I give you an independent set here which picks one thing from each of the color class, why is that an independent set in the original graph? Yes, but you have to be slightly careful, and hence I see that the reduction is slightly wrong. So why do you have to be slightly careful in the backward direction? So you give me an independent set in this graph, okay? See, independent set is a maximization problem. So you're looking for forget that. You're looking for an independent set of size exactly k, right? So you give me an independent set in this graph. Now what if the independent set picks copies of the same vertices? Like it might pick u1 from v1, u2 from v2, and then if it picks copies of the same vertex from this graph, you'll not be able to give me a k size independent set in the original graph. Yeah, this is true. Whatever you give me will be an independent set in the original graph, but what about the size? So for that, let us change the reduction a bit. So what do we want? We want that it should not be the case that there is an independent, like when I give you an independent set in G prime, it should not pick both the copies of this, like it should not pick copies of the same vertices. Let's look at all the copies of U in this G prime. Let's make it a clique. So like look at U is present in the first color class, second color class and the kth color class. Make a clique out of them. That means add an edge between U1 and U2, U2 and U3, U3 and U1 and all sort of edges. Now suppose we did that. Again, let's go back to the forward direction. Will the forward direction go through? If I have an independent set there, I'll again look at the first copy of U here, the second copy of V2 here. That will still be an independent set. Right? And in the backward direction, now whatever independent set you give me, of course that will be an independent set there, and also any independent set cannot pick two copies of the same vertex. So if you give me a k-size independent set in G prime, I'll be able to give you a k-size independent set in the original graph. So this is okay, right? So we have given a reduction from independent set to multicolored independent set. And now let's look at the last thing. Multicolored independent set to dominating set. Again, here we'll be given a graph G of this form and an integer k, and I have to give you a graph G prime and k. So again, let's look at what G is. Okay. So again, let's see what is the dominating set problem. We have to find a set of vertices such that if I take the union of the closed neighborhoods of those vertices, that covers all the vertices. So what is a dominating set? You have to find a set of at most k vertices, let's say this set S, such that if I take the union of all the vertices in S and if I look at the closed neighborhood of those vertices, that is the whole vertex set. This is like another formulation or another way of saying that either you pick a vertex in the dominating set or you pick one of its neighbors in the dominating set. Right? So this is the dominating set problem. So suppose I have this graph, and if this graph has a k-size independent set, and this graph has a k-size independent set, so to begin with, let G prime be equal to this same graph G. Okay, so the G is given as input to this. I have to create another graph G prime for this instance. To begin with, let me give the same graph. See, the point is the inside parts are all cliques. So if I pick one vertex from each inside part, right, and the number of parts are k, then I'll have a k-size dominating set, right, because one vertex from each part will dominate everything inside this part because it's a clique, the neighborhood system, right. So clearly, like, the forward direction is not an issue because every part is a clique. So it doesn't even matter if you give me an independent set in G or not. I can always give you a k-size independent set in the graph that I've constructed if I take G prime to be the same graph, right. But let's look at the backward direction. So suppose you give me a dominating set in G prime, I should be able to give you a multicolored independent set here, right, in G, right. So can I always do that? If you give me some dominating set in G prime, now G prime right now is the same as G, okay. Then, okay, or in other words, when is it that I cannot, when is it that if I give you a dominating set of size at most k, that might not correspond to a multicolored independent set in G? When can that happen? See, what is a multicolored independent set in G? First of all, it has to pick exactly one vertex from each color class. The second is they should form an independent set, right? Now what if, now in G prime, I give you some dominating set. Now what dominating set I give you, that's not in your hands. I'll give you any dominating set, right? What is the guarantee that the dominating set that I give you, first of all, picks at least one vertex from each color class? There is definitely a dominating set that picks one vertex from each color class, but I am giving you something, right? That something could be anything. What if I give you a dominating set that doesn't pick one vertex from each color class? Yeah, so I can give, like, for example, not just that. So for example, there is one vertex in this partition that sees everything here, right? So if I pick this one vertex, this will cover the vertex set of both these parts, right? So I might give you this dominating set of size at most k. Now this will not correspond to a multicolored click. This is one problem, okay. So one problem is I have to ensure that whatever dominating set I am picking from here, it picks exactly one from each color class. So that is one thing that I have to ensure, right. This is one problem. But even if I ensure that, what is the guarantee that the set of vertices that I am giving you will form an independent set in G? Right. I might give you, like for example, suppose these edges are not here now. Suppose I am able to give you a dominating set that picks one vertex from each of these color classes. I might give you a dominating set where these two vertices already have an edge. So this will not correspond to an independent set there, right. So these are the two problems that we have to take care of. The first problem is pretty simple. So again, right now we started with a graph G prime, we set it to G. Now we are gonna add more things, we're gonna add more gadgets to ensure that these problems do not occur. So what kind of a gadget can we add which ensures that any dominating set has to pick one vertex from each of these color classes? Like if it doesn't pick something from this color class, then there's something wrong should happen. So you can play with the budget also, like you're looking for a k size independent set. For example, if you can say that, okay, if a dominating set doesn't pick anything from here, then it has to spend say two more things, or it has to spend more budget to cover some things, some that sort of a thing. So for example, suppose for every color class I add a vertex and I add a new vertex here and I make it adjacent to everything here. So now this is my new graph. In this new graph, this vertex also has to be dominated. Who is going to dominate this vertex? Either you pick this vertex or something from here, right? So now if I don't pick anything from here, then I have to pick this vertex, right? This is one idea. Again, I think you can play with, no, this is one idea, but okay, but suppose I do this. Suppose I add two vertices for every color class and I make both these vertices adjacent to everything in the same color class. So these two vertices don't have an edge between them, but both these vertices see all of V1, for example. Now let's look at a dominating set. Any dominating set has to cover both these vertices, right? And suppose look at a dominating set that doesn't pick anything from V1, then it has to pick both of them, right? Now suppose I did this for all the color classes. For all the color classes, I added two new vertices and I made those two new vertices adjacent to everything in that color class. I did this. And I'm looking for a dominating set of size at most k. Now any dominating set of size at most k, first of all, there is no point of a minimum dominating set of size at most k picking any of these two vertices, because any dominating set of size at most k now has to pick something from each color class, because if it doesn't, first of all, if it doesn't, then it has to pick both these vertices. That can't happen, right? So if I do this thing, like for every color class I added two vertices which see all of V1, then at least I've ensured that if you give me a dominating set of size at most k in this graph, it has to pick one vertex from each color class. It can't avoid a color class completely. This step is taken care of. Now we have to ensure the other thing, that the dominating set that we are picking is indeed will form an independent set in G. Like I should not be picking two vertices in the dominating set which have an edge in G, right? Because I want to, if you give me a dominating set, I want to be able to give you a multicolored independent set in this graph, right? So for that, again, there is a thing that you can do, which is the following. So now you construct G prime like this. You take these color classes V1s and they are clicks. For each of these clicks, you add these two vertices and make them look into all of V1. And now for the across edges, you do the following. Like if G had an edge between say U and V, okay, you don't put that UV edge here. Instead, what you do is, if G had an edge U comma V, if G had an edge U comma V, then you look at U here and V here, create a new vertex for this edge, as in let's call this vertex V of UV. So for every edge UV, we create a new vertex and we do the following. We make it adjacent to, like if suppose U was coming from here, V was coming from here, we make this UV adjacent to everything in this color class except V, and we make this W adjacent to everything in this color class except U. And why have we done this is because, see, we wanted to say that UV was an edge in G and we want that no dominating set should pick both U and V. This is what we wanted, right? Now suppose there is a dominating set that picks both U and V, okay? Then note that, and the budget is K. We know any dominating set has to pick exactly one from each color class. So if from this color class it has picked U, it can't pick anything else. From this color class it has picked V, it can't pick anything else. But if this is the case, then who is going to dominate WUV in this graph? Because WUV has edges to everything except U and V. So if there is a dominating set that picks U from here and V from here, it can't pick anything else because of the budget, and hence it can't dominate U and UVW. So if there is a dominating set of this graph, it has to dominate W of UV, then it has to pick, if it picks U from this, then it cannot pick W from there. Because, so if it picks U from here, it can't pick V from here, because then it will not be able to dominate this VW, right? So this is the final reduction. Now let's just quickly see, if I give you a multicolored independent set in this graph, that is definitely a dominating set here, because multicolored independent set will pick one vertex from each color class, and the same set will form a dominating set here, because if I pick one vertex from each color class, that's a dominating set. And in the reverse direction, if I give you a dominating set in G prime, we just noted that that dominating set, if you're giving me a dominating set of size K, then that dominating set picks exactly one vertex from each color class. That is true because we added these sort of vertices. And this dominating set, it cannot be the case that two vertices in this dominating set have an edge in the original graph, because if they did, then this vertex corresponding to that edge will not be dominated. And hence this dominating set that you are giving me picks one vertex from each color class and is an independent set in this G, right? So basically this is the reduction. I did it a bit quickly, but this is the construction. You can again go back and sink this in. And let us just quickly see if it's a parameterized reduction. How much time did it take? How much time does it take to compute G prime from G? You just take the same color classes, add two vertices for each color class, and then for every edge add this VW, some polynomial time, right? What is the size of G prime? It's basically n plus we had one vertex for each edge, so it's some n plus m. It is some polynomial in the size of G, right? And here K goes to K, so it is indeed a parameterized reduction, right? And hence, because of this, since click can't have an FPT algorithm, independent set can't have an FPT algorithm, this can't have an FPT algorithm, and hence this can't have an FPT algorithm.